Hello, everyone. Welcome to our lecture on machine learning interpretability. In today's lecture, we are going to continue the global interpretability techniques. In the previous micro lectures on the topic of machine learning interpretability, we introduced the concept of interpretability and we showed its importance. We differentiated between model interpretability and model accuracy, and we explored key approaches to explaining machine learning models, and we introduced key global interpretability techniques. After completing this micro lecture, you will understand another few examples of global interpretability techniques. So today we are going to continue the topic of global interpretability techniques. Last week we covered partial dependence plot and individual conditional expectations, and today we are going to cover another 3 techniques. So the third technique that we have is called accumulated local effect. And the accumulated local effect solves the problem of the partial dependence plot. So when we have correlated features in the previous lectures, we saw the partial dependence plot can generate some unrealistic instances, and hence it can give us some misleading idea about the influence of the feature on the predicted outcome. And in order to solve this problem, here we have the accumulated local effect. So the accumulated local effect, it's another way for explaining the global behavior of the model, and it's calculated as follows. So assume that we would like to understand the impact of feature x1 on the predicted outcome. So what we are going to do is simply divide the feature. So we split the feature into intervals. So here we split the feature x1 into 5 intervals. And for each of the instances here that we have in our training data, we are going to do the follows. We are going to compute the difference in the predictions when replacing the feature value, which is x1, once with the lower bound of the interval and once with the upper bound of the interval. And we are going to repeat the same for all the instances here that we have in our training data set, minus the mean effect, which is the mean prediction across all the instances here that we have in our training data set. And that will give us the accumulated local effect. So let us first try here to understand how can we interpret the value that we get from the accumulated local effects. So assume that we calculated the accumulated local effect and we get a value of -2 when we try to understand the influence of feature xj on the predicted outcome. What does that mean? So for example, when we try to understand the impact of feature xj at value equal 3, we got -2. That means that when the feature, which is xj, is 3, that means that the prediction is 2 units lower than the average prediction of the machine learning model. If it's a +2, means that it's higher than the average prediction by 2 units. So this is how we can interpret the value of the accumulated local effect. Let us see how the accumulated local effects can solve the problem of the partial dependence plot. And let us also consider the same example we considered in the previous micro lecture. Assume that we would like to predict the price of the house given the number of rooms and also given the living area. And we would like to understand the impact of the living area when it's equal 30 on the predicted outcome, which is the price of the house. So here what we are going to do is that we are going only to use the houses within a specific interval. And in this interval, we are going to have houses with a very similar area, something like between, for example, 29 and 31. So in this way, we are going to generate some realistic instances, unlike the case with the partial dependence plot. So simply, the accumulated local effect solves the problem of the partial dependence plot and isolates the pure impact of the living area and prevent mixing the effect with influences from other correlated features. The next technique that also provides global explanation and the global interpretation for the machine learning model is called feature importance. So the idea of the feature importance is very simple. Assume that we have two features, x1 and x2. When changing the value slightly of the feature x1, the performance changes significantly. But when we change the value slightly of the feature x2, the predictions, it changed slightly. What does that mean? That means that feature x1 is more important than feature x2 because a small change in the feature value can result in a significant change in the model performance. So this is simply how can we calculate the feature importance and identify the most important features that impact the prediction. So let us take exactly the steps. How can we calculate the feature importance using feature importance algorithm? So here we have a trained machine learning model, the black box model, in which we are trying to explain f hat. And we have here feature matrix X, and we have a target vector Y. And we estimate the error, for example, using a particular loss function. And here we estimate the original model error, E original. So this is L is the original error of the black box model. And in order to estimate the importance of each of the features we have in our machine learning model, we repeat the following steps. So the first thing is that we generate a feature matrix X perm by permuting the feature J in the data X. This breaks the association between feature J and the true outcome Y. And then for each of the instances that we generate in matrix X, we calculate the loss, E perm, for each instances, based on the predictions we got from the black box model. And then we calculate the difference in the error between this error, the first one, E original, and E perm that we calculated from the previous steps. So simply the feature that has a larger permutation feature importance means the feature that has the higher difference between E perm and E original is more important than others that have a smaller difference. The last step is that we sort the features in a descending order based on the F1 here that we calculated in this step. So now let us try to visualize the feature importance exactly on the same rental Bickel data set that we considered in our previous micro lecture. On the top of this rental bike data, we fit a support vector machine model, and we are trying to explain this model globally using the feature importance. And this is here in this figure, we can visualize the feature importance for all the features used in training the machine learning model based on the support vector machine. So on the x-axis, we have the feature importance. On the y-axis, we have the features used in training the support vector machine model. And it's clear here that a feature like a temperature is the most important feature for the support vector machine model. And also it's clear that something like holiday, it's the least important one. So the last technique that we have for today's micro lecture is a technique called global surrogate model. This is another way to explain the global behavior of the model. The idea is very simple. We have a black box model, and this black box model is making predictions. What we are going to do is simply we are going to fit interpretable model based on the original data and the predictions that we got from the black box model. And we are going to provide the explanations based on the interpretable model we fitted on the data. So let us try to have the steps of the algorithm so it will be clear. So we are going to start from a data set. This data set could be the data set used in training the black box model or another data set that's somehow coming from the same distribution. And the second step is that for this data set, we are going to get the predictions from the black box model. And next step, we are going to use an interpretable model. It could be a linear model. It could be a shallow decision tree model. The next step is that we are going to train this interpretable model on the top of X and the predictions we got from the black box model. then that's it. We are done. We have a surrogate model. But in order to know exactly whether or not the surrogate model is good or bad, we need to understand exactly how well the surrogate model can approximate the behavior of the black box model. To do that, we calculate the R square that shows us how well the surrogate model can replicate or approximate the behavior of the black box model. So R square is calculated as 1 minus SSE divided by SST. So SSE is simply the sum of square error, and SST is the sum of squares total. And it's calculated as follows: 1 minus the sum over all the instances that we have in X. And here we have Y I hat star. This one is the predictions that we got from the surrogate model for instance I. And I hat bar, I hat Y, sorry, hat I is a prediction of black box model, and Y hat bar is a mean of the black box model prediction. This is simply how we can calculate R squared. And the value of R squared between 0 and 1, the higher is the better. So 1 is like, means that the surrogate model that we have is very good, is excellent in approximating the behavior of the black box model. Smaller value for R means that this model is not that good in approximating the behavior of the black box model. So this is here a visualization for the global surrogate model approach. So here the black box model that we are trying to explain is a support vector machine. Again, is trained on the bike rental data that we explained in the previous micro lecture to predict the bike count. And the surrogate model here that we build on the top of the original data and the prediction from the support vector machine is a decision tree. And here also we calculate the R square, and it was 0.77, indicating somehow good approximation for the support vector machine behavior. And the insights that we can get from the figure here we have is that rented bikes counts increase when the temperature is above 13. And also another interesting insight is that bike rentals are higher later in the 2 years with a significant cutoff at 435 days. Thank you for listening.